We finally made it to Unit 6, which is about linear functions. And I know that we just finished an entire unit on linear functions, but in this unit we're going to take linear functions further. We're going to start looking at the relationship between the variables that are in the function and also taking a look at what kind of relationships there can be. And this will also lead us into a little bit of statistics. So we're going to start with linear relationships. And linear relationships are obviously those relationships between those variables that when you graph it give you a straight line. And this should make sense because we've done a lot of work with the word linear. Linear means line. So anytime we're talking about anything linear, you of course should be talking about getting a straight line when you graph it. So now let's take a look at a couple examples. So here we have a linear relationship. A car drives at 50 miles per hour. So if we graph that, we of course always put time on x. So these are our hours. And then we're going to put our miles on y. So if he's going 50 miles every hour, we can just graph that. And remember, we get to choose essentially how much they go up. So maybe I want my hours to go up by 1. So 1, 2, 3. And maybe I want to have my y go up by 50 because that'll make it nice and easy. So now that I've done that, I just need to take a look at my information. Every hour, he's going 50 miles per hour. So at 1 hour, he'll be at 50 miles away. At 2 hours, he'll be 100 miles away. 3 hours, 4 hours, and we can see a general trend that's going to happen. Now let's draw our line. And we put an arrow at this end because it can go on for forever. Obviously, he's probably not going to be driving for that long, but you never know. It might be a road trip. So this obviously is linear. When you graph it, we have a straight line. So this is also a linear relationship. There is a relationship between the variables. So we have a relationship between the hours that he's driving and the distance that he's covered. We can see that the amount of hours he's been driving is going to correspond with the amount of miles he's covered. We can see exactly that at 7 hours, he's done 350 miles. Now, the reason this is linear is because they're always going to correspond together and go up consistently. They're both consistently going up. If one goes up, the other's going to go up. So if I'm talking about more hours, we're going to have more miles traveled. Or if I'm talking about less hours traveled, we're going to have less miles. So that's why we have a positive slope that is linear. So we can see that graphing linear relationships is nothing new. It's just graphing that equation and graphing that situation. We've done that before. But how do we determine if a situation is a linear relationship? Well, let's take a look at some examples of situations and decide for ourselves if it would be a linear relationship. So this first example here is height off the ground and your time on the Ferris wheel. So we're trying to see if your height is always going to be a linear relationship with the amount of time you spend on a Ferris wheel. So essentially, could we draw some sort of linear graph with that? So maybe it's positive or maybe it's negative. Can we draw some sort of linear graph that goes along with this situation? Is there always a consistent that the longer I'm on the Ferris wheel, the higher I'm going to be? Or is there a consistent the longer I'm on the Ferris wheel, the lower I'll be? Well, maybe for the first 2 seconds, but then it always goes back down, right? Because it goes around and around and around. So no, if I spend 3 hours on a Ferris wheel, it doesn't mean I'm going to be hundreds of miles up. There isn't that linear relationship of the longer I'm there, the higher I'm going to go. So this is not a linear relationship because we have neither of those kinds of graphs. What about the second one? Amount of water in a bucket that is being filled and time. So we're trying to see if there is a corresponding between the amount of time that's happening and the amount of water in a bucket. So this bucket's being filled. So as time goes on, would I expect the amount of water to also go up? Yeah, actually that makes sense. The water coming out of the hose is probably coming out at a consistent rate. So the longer I'm waiting, the water in the bucket's going to slowly rise. So the longer I'm filling it up, the more water is going to be there. So I'd say, yeah, that sounds like a linear relationship. What about this last one? The amount of popcorn left in the bucket and the time at the movies. This is a common situation for most of us. We sit down with our bucket of popcorn and we just start eating. Normally at a fairly constant rate because we don't even notice it because we're watching the movie. So let's see. Over time, the amount of popcorn in the bucket. Now, is this going to be going up? It'd be nice if the popcorn amount could increase, but of course that's not going to happen. As time goes on, the amount of popcorn in my bucket should go down. As long as it's a fairly consistent rate, this is going to be a linear relationship because as more time goes on, I'd expect the popcorn amount to go down. So hopefully this made you see that linear relationships do not always need to be positive, have a positive slope. You can also have a negative slope. Things can be decreasing with time or with whatever it's in a relationship with. Now we're going to take a look at a bunch of different graphs and identify which one makes sense with the situation. So essentially saying which one of these would be the graph to this situation. So the situation is the more candy you buy, the more money it costs. Makes sense. If I'm buying, 5 bags of candy, maybe it costs $5. And then if I buy 10 bags of candy, it should cost obviously more, like maybe $10 as well. So we need to figure out which of these graphs make sense. Should I have this positive slope where they both go up together? Should I have this kind of steady slope of nothing happening? Or should I have a decreasing slope where one goes down as the other goes up? Well, we kind of just said that both are going to go up. In fact, you kind of have these key words that both are more. The more you have of one, the more you're going to need of the other. So they're both increasing together. So that's actually going to be this first one right here. They're both going to be increasing together. The more candy I buy, the more money I have to spend. Let's take a look at another example. This next situation says the amount of water sitting in a bucket over time if nothing happens to it. So we're not given much data. We don't know if the bucket's being filled or it's being drained, but we do kind of are told that nothing is happening. So we're talking about the relationship between amount of water and time, but we're not given much information of that they're both going up together or both going down together, but we are kind of given the information of nothing is happening. I'm actually going to let you finish this one on your own. So thinking about the fact that nothing is happening, so no more water's being added, no water's being taken away, which one of these is the graph to show the relationship between the amount of water and time? Go ahead and finish that one up. All right, we get to talk again about rate of change and the initial value. I know we've talked about it a lot, but we're just bringing it back because we're going to be talking about it in the context of specific situations. So let's get down to the definition again of rate of change and the initial value. So rate of change, you should remember, is essentially the slope, how often something's happening. And a lot of times we'll see it as being the speed of which something's being filled, something's being drained, someone is traveling this amount. The initial value is just whatever starting amount we have. So it could be we're filling a bucket, but the bucket already has 2 inches of water in it. Or I'm going to have a race with someone, but they're starting 5 feet ahead. Or I need to go to a store like Costco, but they charge you just to get in the store. So that's the initial value that I have to spend without actually even buying anything. So now that we've reminded ourselves what those are, let's take a look at how to identify those within the context of equations and graphs. So here I have this equation, y equals negative 3x plus 5, and I want to identify the rate of change and the initial value. Now the rate of change is the same as the slope, and we know how to find the slope from an equation. It's always the number in front of x. So in this case, the rate of change, the slope, is negative 3. So the rate of change is negative 3, so it's decreasing 3 every 1. We don't know what the relationship is between if it's time and miles or whatever, but whatever's happening is decreasing by 3 by the other one increasing by 1. Now, normally if you can identify the rate of change, you can automatically identify the other one because it's the last number. So the initial value is always going to be whatever's being added or subtracted at the end. So it's whatever being added or subtracted in the equation. So for us, we have this plus 5 right here, and that's going to be our initial value. So for this equation, we don't know what the situation is, but we know that we're starting at 5, and then we're actually going down 3 over 1 every single time. Here we have this another situation. We have another equation where we have y equals a 2 over 3x minus 4. So I'm going to let you finish this one up. Identify the initial value and identify the rate of change in that one. Let's take a look at some graphs. Let's see if we can identify the rate of change and the initial value. Now, the rate of change is essentially the slope, right? It's the up and over. So we're given 2 points. So we can see that we go up 3, and we're going over from 12 to 18, which is 6. So we have a rate of change that's a 3 over 6. And since we know how to reduce our fractions, we know that that actually means it's a 1/2. So we're actually going up 1 over 1/2 every single time. So we have our rate of change, which is a 1/2, and now we just need to find out the initial value. And that's just our starting point over here. So remember, the initial value is our y-intercept, where it crosses the y-axis. So that looks about like 8. So we identified our slope, our rate of change, and our initial value, which is our y-intercept. So let's take a look at one more graph. Here we have a linear relationship between the size of a baby and its growth period. So obviously as time goes on, the baby hopefully should be growing and getting bigger. That makes sense. So we have an initial value, you can see it right here, and we have a steady slope. Now I'm actually going to let you calculate this one on your own. So remember, your rate of change is your slope, how much up over how much over, and your initial value is our starting point right here. And I'm going to let you finish that one up. And that is actually the end of this lesson.